Okay, so now let's talk about a fight that you're about to enter in that you will be in for the rest of your career for as long as that you're in aviation. Now, that's the fight against corrosion. Corrosion, you can think of it a lot like if you have a piece of wood and it rots, corrosion is the rotting of metal. It effectively is a chemical process where valence electrons get shed away from the metal alloy that you want to be in good working condition, and it goes and it forms its own thing, oxidation or white chalk or whatever, depending on the type of metal that it is. This is something that you're going to constantly be inspecting for. It's something that can cause massive damage to an aircraft without it ever crashing. It's sitting out there. It's literally rotting if it's not taken care of. You're going to be looking for it on every inspection that you go in. You're going to have to combat it. You're going to have to do things to prevent it from happening. You're going to have to do things to fix it whenever it shows up. Like what do we do with this corrosion? Do we replace the piece, or do we somehow treat the metal so that way we kill the corrosion and it doesn't come back? So let's talk about some corrosion basics. Then we're going to get into some corrosion types, and then we're going to kind of flow on from there and apply it to aircraft maintenance. All right, so corrosion, it needs three things. It needs a metal to corrode, oxygen to facilitate the chemical reaction, and then water, an electrolyte. Effectively, you will always need those three things in some shape, form, or fashion to begin the corrosive process. So you begin to wonder, it's like, well, how does the Navy manage to keep ships afloat if they need that? Because Navy ships are made out of metal. They definitely have a lot of oxygen. They're in the atmosphere, and they're floating around in H2O, so there's oxygen in the water. And then there's water. They float on water. Well, one of the primary things that you'll see Navy sailors doing is removing paint and repainting. Gets after the metal bit. They put a protective barrier over it, and then it just takes the metal out of the equation because the metal can no longer access water or oxygen. So paint becomes one of our primary strategies to combat corrosion. And then you have corrosion inhibitors that go onto it as well. But no matter what, you always need those three things, the parts of the corrosion triangle. Okay, so what are some other factors that we need to take into consideration with corrosion? All right, so AC 43-4 is the FAA's kind of like corrosion Bible. Pretty much anything you want to know about corrosion is going to be in there, and it's updated fairly frequently as new things come to light. But they list 12 things that can affect corrosion. Those are the type of metal. So some metals corrode differently. All metals corrode differently, but some of them corrode way worse than other ones. So if you think of like titanium corrodes, but it is extremely slowly. So that's one of the reasons why titanium is a kind of a preferred metal because it's naturally kind of corrosion resistant. Whereas if you look at like iron, it will corrode before you even put it on the airplane. Like you'll start to see that orange oxidation start to show up. Aluminum is more like titanium. It's slower, but it does do it. It'll pit and it can be pretty bad. But types of metal is a factor. Heat treatment and grain direction. So there's different heat treatments. If you go back to our metallurgy talk about different grades of and different types of aluminum, all of that actually factors into its corrosion properties. Sometimes certain metals can corrode a lot faster than other metals based on the way in which that it was annealed and manufactured, poured, and then treated later on, because of the way that the electrons at the molecular level are being arranged. If you make it so that way it's very easy to shed electrons, it's going to corrode a lot faster. If you make it in such a way that it's a little bit more difficult because its geometry has changed, well, that's going to corrode a little bit slower. Okay, presence of dissimilar, less corrodable metal. So remember, This is effectively, it's just simply the shedding of electrons from one place to another, all right? So if you have substance A that has a lot of blank spaces in its atomic orbit where it can capture a lot of electrons, and you have substance B that has a lot of electrons, well, the guys that are trying to leave the concert are going to go to the empty concert. They just want to get out. So they're going to go, you're going to have electrons go from like this super overpopulated atom to go to this super underpopulated atom, and you're going to have a lot more corrosion. So anytime you see dissimilar metals, know that that's happening, because there's a imbalance no matter what. No matter what metals they are, they're going to be different, and there's going to be like kind of this cross-pollination of electrons as it goes. So you'll see a lot of washer stack-ups that are built to try to help combat this. You'll see plastic washers, and you're like, why is there a plastic washer here? Well, it's there. It's because they're trying to minimize the surface area between two dissimilar metals, so that way there's even less of a chance of corrosion happening. It's not totally effective, because at the end of the day, a lot of times those are screws and bolts, and those screws and bolts are, of a certain type of metal going into another certain type of metal, and it is what it is, and that's where like inspection and maintenance comes into it. There's just nothing you can really do about it if you're going to use those two metals. That's just, that's life. So dissimilar metals, keep that in mind. Anodic and cathodic surface areas in galvanic corrosion. And we're getting to that's a little bit meatier, so we'll get into that here in just a minute about how how the process actually works and what that means for factors affecting corrosion. Temperature. So generally speaking, the warmer things get, the faster they corrode. Now there's some nuance to that, but effectively, the warmer it gets, the faster it corrodes. So you'll see corrosion a lot in like tropical areas. So it's kind of like, the kind of trade-off. The trade-off, so if you notice that like you'll have a lot of aircraft boneyards in deserts. Well, so the heat doesn't help the corrosion, but the lack of water in the air absolutely helps. It slows corrosion down. It also ratchets up electrostatic discharge, so it's not really good for avionics, but for the rest of the airplane, it's actually really, really good. You won't see boneyards in a tropical environment, or say like in Niger or Cameroon or someplace like that, because the water content is up and the heat is up. It means things corrode really, really, really fast. It's effectively like a rotting yard for airplanes. You don't want that. Okay, presence of electrolytes, hard water, salt water, battery fluids, so on and so forth. So this is like why you'll end up doing, if you end up flying over salt water, you'll end up doing engine washes on a regular basis, because as the engine flies around, it's soaking up all of that salty air, and that's getting on the blades inside the turbine, and you need to do a freshwater rinse to get it out. So you'll end up shooting it up with some soap that basically is a corrosion inhibitor that goes over the blades, and you'll dry run the motor, just let it suck it all up until it starts coming out. Then you'll do a freshwater rinse to try to blow all that soap out. And so that way, like, it helps inhibit that corrosion. You'll do any number of inspections if you're operating around salt water, seawater, anything like that, or in a water-rich environment, say like a rainforest or whatever. You'll be constantly doing corrosion stuff. Now, where it mentions battery acid, it's a direct chemical attack, and that's one that can really ramp up the corrosion pretty quick, because the battery acid is built so that way it's highly reactive and has a lot of like electrons to get rid of, and it's that's what its whole thing is. That's how a battery works. The problem is that whenever that sulfuric acid gets on the airplane, it just eats the airplane up. And what's happening there is that chemical exchange between those dissimilar metals, in this case an acid and a metal, it's going to eat the paint away, then start reacting with the metal, and that's going to create rampant corrosion. And there's been more than one airplane I've seen with old lead acid batteries that somebody turned too hard, did some kind of thing that they weren't supposed to do, the battery came loose, battery acid goes everywhere, and then it just eats the whole back end of the airplane up. So you don't want that. That could be really, really bad. Availability of oxygen, so a part of the corrosion triangle. Well, you have to have oxygen, so that's why painting becomes like this like really important thing. Even aircraft that just roll off the line, then they will cure them with a corrosion inhibitor. It's like this green tacky stuff, and then whenever they go to paint, they put a solvent on it, takes the tacky stuff off, and they prime it and they paint it from then on there. But the point being is that dissimilar, or just like bare naked metal is never a good thing. Even whenever you receive brand new sheets of sheet metal, it'll have a film on it that keeps the corrosion from happening. And what you're trying to do is create a barrier between the metal and the oxygen in the atmosphere. And if you can do that, you can deal a pretty serious blow to corrosion. So that's one thing that you'll always want to keep in mind when it comes to painting. Okay. Presence of biological organisms. So if a bird makes a nest inside the airplane, it's going to do its business wherever it's at, and then that business is going to have a dissimilar chemical in it on the aircraft itself. If it touches any metal, then you're going to end up having a reaction. That reaction is going to be corrosion. Okay, mechanical stress on the corroding metal. All right, so mechanical stress, it stretches things. If you look at, like, you think about my hand as a piece of metal, as it stretches out, you see those gaps that form? Well, oxygen, other material can get in there and start causing corrosion. And that's why you'll start to do a lot of corrosion inspections on high stress places. So earlier we talked about my experience with the 58 and the tail rotor gearbox having that little plate right there. That plate was also like very susceptible to corrosion. That whole area was, and the reason being is the strain that's constantly being put on it, stretching the metal and creating new areas. So you have to reapply paint on a pretty regular basis to make sure that that it's painted, because as it starts to stretch, then the surface of the paint starts to crack. As it starts to crack, it allows things to come in there and that can get corrosion going. Okay, time of exposure to a corrosive environment. So that goes back to the engine washes. That's a kind of a time of exposure type thing. As it flies within 10 nautical miles of a saltwater body, then you're exposing it to that super salty air. The salt inside the air just adds to the corrosion. It's more or less like sucking up a very weak battery acid, really. And so you are exposing it to that area. The same idea with the old boneyards, that we can mitigate this risk if we park them someplace that doesn't have a lot of oxygen or doesn't have a lot of water in the air, which will slow the corrosive process down, because we're taking a leg of the corrosion triangle out. So the area that it's in can be very, very important. Lead and graphite pencil marks on aircraft surface metals. So generally speaking, you don't ever want to mark on an aircraft if you can help it. Reason being is that graphite has a certain amount of electrons, has a certain chemical construct, and the metal has a certain chemical construct with a certain number of electrons. And guess what? They're not the same. So they're going to want to exchange metal, and that's going to cause corrosion. The last one is laboratory and like any sort of like aircraft water systems leaking. Labs in heavy commercial airplanes are really bad about leaking, and they have blue water, so it's made to have certain properties, so that way whenever you use the bathroom on an airplane, it doesn't like stink everybody out. But that blue water has certain chemicals in it that cause corrosion if it gets loose. So it has to be really tightly contained and inspected to make sure that it's not leaking everywhere, because not only is leaking blue water bad for electronics, it's also really bad to be on metals as well. Okay, so let's talk about the different types of corrosive attacks you could have. You could have a direct attack and an electrochemical attack. A direct attack is pretty simple to identify. It's like battery acid getting leaked onto metal, or some brazed joint with a bead that flew off, and now that spot's starting to corrode, or whatever. It basically means that you have like a metal, and then you have some sort of chemical going on to said metal causing corrosion. Most of the time on modern airplanes, this is the type of corrosion that you will generally see, and it's usually from something that somebody spilled somewhere or got careless with, or something like that, because it's engineered with corrosion in mind to try to keep corrosion from becoming a thing. And so that's where like sealed batteries comes in. That really kind of helps curtail a lot of corrosion that's happened in the past. So like that's a direct chemical attack. An electrochemical attack, though, is the more natural form, that like all wood wants to rot, all metals want to corrode, and eventually that will happen given enough time and the right circumstances. And so you'll always have to be inspecting all metals for that. But especially metals that are in like high stress areas, have dissimilar metals, all the types of things that we talked about. Those are all just like, things that just add to the risk of corrosion and things that you need to pay attention to. So yeah, so direct attack, electrochemical attack, and know the difference between the two. One involves throw battery acid on it. The other one involves basically, if it just sits there long enough, an electrochemical attack will happen in some way, shape, form, or fashion, because there's something touching it in some way, shape, form, or fashion, causing it to corrode, because that's just life. That's how life goes. Okay, so let's talk about the different types of corrosion and how we identify them. There's several of these, and you will see all of them in one shape, form, or fashion. So first off is surface corrosion. That's pretty simple. If you've ever had anything, you have an old car that's made out of iron or made out of some sort of steel, you'll see orange oxidation start to film, and so start to form. That's a pretty standard, life experience that we should all be able to identify with. But surface corrosion is general surface corrosion, the most common form of corrosion. It appears as a general roughening, etching, or pitting of the surface metal, frequently accompanied by a powdery deposit of corrosion products. Depending on what it is, you'll end up having different types of manifestations of corrosion. So like iron, it manifests in orange, brown oxidation. Copper, like Statue of Liberty, is actually supposed to be bronze, turns green. You walk around town and see like the old copper flashing on roofs, and they're almost always green. You go over to Europe or the Northeast, you'll end up seeing those types of manifestations of corrosion. So aluminum's also will have this like white powdery substance. That's how you know what corrosion looks like. If it's not shiny and it has like kind of this like gray haze over it, that's corrosion on the surface of the aluminum. All right, filiform corrosion. So filiform corrosion is a special form of oxygen concentration cell that occurs on metal surfaces having an organic coating system. It's recognized as its characteristic worm-like trace of corrosion products beneath the paint film. Okay, so filiform corrosion is corrosion that appears in like a worm-like fashion. So you'll end up having like a scratch on a piece of aluminum that exposes the metal to the air, and then corrosion starts to happen. And what will end up happening is that like you'll have a point of origin, and the corrosion doesn't just go straight out, and it doesn't like go into a nice uniform wave. It just kind of meanders, and it's doing that all up and down that scratch. And so what it ends up looking like is like this like almost spider webby kind of corrosion. But you'll see it, and you'll see where the original damage was at, and where the filiform comes off of it. So that's filiform corrosion. Okay, so pitting corrosion. Pitting corrosion is probably the worst on a metal because if it's under strain, that becomes like a weak point in the metal, and that's where breaking will happen. But essentially pitting is just that. It creates pits on the metal. Aluminum is really bad about this. You can definitely have it on just about any form of metal, but aluminum seems to really pit. At least in my experience, seems to like, whereas iron definitely pits really, really bad as well. And you can go find like an old truck or whatever, run your hand on it, so super rough. Okay, dissimilar metal corrosion is extensive pitting damage that result in contact between two dissimilar parts in the presence of a conductor. So essentially you would have like aluminum and iron that are touching one another, and then they get wet, and then you'll end up having dissimilar metal corrosion. Okay, so concentration cell, also known as crevice corrosion, is corrosion of metals in a metal-to-metal joint, corrosion at the edge of a joint, even though the joined metals are identical, or corrosion of a spot on the metal surface covered by a foreign material. So think about like a butt joint that's like at a 90 that has like a little crack in it, and things start to pile up in there, and that junk or that dirt or dust or whatever leads to concentration cell corrosion. A lot of times water kind of goes to its lowest point, and then you'll end up having corrosion at that point. So that's a concentration cell corrosion. Intergranular corrosion. This type of corrosion is an attack along the grain boundaries of an alloy. It commonly results from a lack of uniformity in the alloy structure. Aluminum alloys and some stainless steels are particularly susceptible to this form of electrochemical attack. The lack of uniformity is caused by changes that occur in the alloy during the heating and cooling process of the materials manufacturing. So essentially, as if you're buying kind of like subpar aluminum, where they rushed through the process or they didn't let it cool correctly, and the grain of the aluminum shifted, that shift in grain can be a place for intergranular corrosion to happen. That's corrosion that happens inside of the metal itself and then corrodes out. And so it's probably one of the more dangerous forms of corrosion, but it's also one of the more rare ones. You generally won't see it, and whenever you do, it's a big deal. You're going to have to replace all of whatever is attached to that. Okay, exfoliation corrosion is an advanced form of intergranular corrosion that shows up by lifting the surface grains of the metal by force of expanding corrosion products occurring in the grain boundaries just below the surface. So essentially, this is like a cyst inside the metal. Like you have intergranular corrosion that's happening, you don't see it, but then all of a sudden it starts to produce. And corrosion is a process that produces a product at the end of it. Like on iron, it's oxidation. On aluminum, it's like that white chalky substance or whatever. But whatever is happening there, it's starting to create like more or less like a big boil or a cyst or a pimple, and it boils up, and then you can lance it and all that white stuff's up in there. But that's an exfoliation corrosion. It's pushing it out. Stress corrosion or cracking. We've already kind of gone over that. That stress corrosion occurs inside of areas that cause the metal to fatigue because of those different reasons. Okay, fretting corrosion. That's an interesting one. Fretting corrosion is particularly damaging from a form of corrosive attack that occurs between two mating surfaces, normally at rest with respect to one another, and are subject to the slight relative motion. It's characterized by pitting of the surfaces and the generation of considerable quantities of finely divided debris. Since the restrictive movements of the two surfaces prevent debris from escaping very easily, their extremely localized abrasion occurs. So fretting corrosion is you'll end up having. So with fretting corrosion, you'll end up having like rivets that are they're like smoking rivets. You'll see all this kind of like black chalky stuff coming off of it. That's where you end up getting fretting corrosion the most commonly. It can be in other areas as well. Anything that meets that criteria will cause fretting corrosion given enough time. Fatigue corrosion is another one. Fatigue corrosion involves cyclic stress in corrosive environments. That's like our Hawaii flight 243. That like it was constantly overstressed in the saltwater environment. Eventually, if corrosion starts to happen, causes a weakness, boom, off it goes. Fatigue corrosion occurs in two stages. During the first stage, the combined action of corrosion and cyclic stress damages the metal by pitting and crack formations. That's where you should find it at. And it's completely removed. The second stage is essentially a fatigue stage where the failure proceeds by the propagation of a crack. So essentially stage one is like you start to see the corrosion. Stage two is the corrosion starts to crack the metal that it's in. Okay, galvanic corrosion is when two dissimilar metals make electrical contact in the presence of an electrolyte. So essentially, like if you have your iron and your aluminum are touching each other, and then you splash salt water on it, you're going to get galvanic corrosion. Okay, so before we wrap up our different types of corrosion, let's talk about some common corrosive agents. You have acid, alkalis, salts, atmosphere, and water. So water is something you're going to have to deal with because you're going to have to wash the aircraft. You're going to have to deal with just water in the atmosphere, just flying. It's going to get wet. I mean, airplanes all get wet on the outside, period. So you're going to have to deal with that. Atmosphere, obviously, different atmospheres will change. So if you're down in Gulf Shores and you're parking, so like you fly down to Dauphin Island, Alabama, there is a little strip literally right next to the ocean. That's going to be a very corrosion heavy environment because it's literally right beside the sea. A lot different than say if you flew into Durango, Colorado. That's like way up. It's a lot thinner, and there's no real moisture in there most of the time, or if you go down to like Victorville, there's no moisture in there. That atmosphere would be a little bit more conducive to not corroding as opposed to Dolphin Island, which is going to corrode a lot. Other ones, salts, obviously being next to salt water is a big deal. Being inside of big cities, they have a lot of smog. So like if you flew into Beijing right now, you'd end up having a corrosion issue, or you could have a corrosion issue if you're doing it on a regular basis, because it's going to that smog is going to absolutely eat up the airplane if left unchecked. Alkalis are not as corrosive as acids. Aluminum, magnesium, and alloys are extremely prone to corrosive attack by many alkaline solutions. So like this could be anything from like wood ash to cement dust. Anything that's high in alkali will cause corrosion. And then of course acid, we've already talked about that pretty extensively, like battery acid and that sort of thing. You'll end up having corrosion that way. So yeah, so that's types of corrosion. Okay, so before we go a whole lot further, let's talk about the effects of corrosion, like what could potentially happen. So you could potentially just simply have to replace some parts. Or maybe there's just some corrosion it's caused some pitting in an aircraft, and what you're trying to do is just take a wire brush, clean off whatever's there, re-expose the metal, and then put a corrosion inhibitor on it and maybe paint it. And maybe that's all that happens. Or it could be like Hawaiian Flight 243, which cost an airline stewardess her life.
Around 2 in the afternoon on April 28, 1988, Aloha Airlines Flight 243 makes an emergency landing at Kahului Airport on Maui.
What really got us was people strapped in the seats, not moving. They're just arms dangling in the air, hair flying in the wind.
The top of the Boeing 737 peeled back like a canned good, turning the plane into a convertible. The plane had left Hilo and was heading to Honolulu when about 20 minutes into the flight, there was what sounded like an explosion.
I thought this was it, because I thought we lost the pilot and everything, because from my angle, I only saw sky.
Then looked to my other side, with my right side, and no walls. I looked at my feet, and I noticed that right next to my feet was just an exposed area, and I could see the ocean below me.
I was working in my seat in the back of the Aloha Airlines, and all of a sudden there was this loud noise. I heard an impact, looked up, and I saw that the plane was falling apart up in the front. Thought we were done.
So this is something to take very, very seriously, because the effects could be insane. So now that we kind of have a baseline for like what corrosion is and what the consequences of corrosion could potentially be, let's talk about the two different types of corrosive attacks. Okay, so let's talk about corrosion-prone areas in aircraft. We're just going to kind of go down the list, and we'll splice in different examples from the Lear or the Aztec on there. So exhaust tail areas. So both jet and reciprocating engines exhaust deposits are very corrosive and give particular trouble where gaps, seams, hinges, fairings are located downstream from the exhaust pipes or nozzles. I'll tell you, that's probably your number one corrosion find is going to be exhaust pipes, especially on recip engines. They will end up having all kinds of metal oxidation all the way down the pipe all the time. You can think about it, right? So like it's carrying corrosive elements that's coming out of the exhaust stroke on the engine, and it's getting all up and down that pipe. Then it's going to get hot, really, really hot, and then cool off. And that expansion and contraction causes cracks, which will eventually lead to absorbing more of that corrosive element, and leading to more corrosion. So it only makes sense that our exhaust is like number one on the list, because that is the most corrosion area on the aircraft. Okay, battery compartments and battery vent openings. Old lead acid batteries, for sure, corrosion, 100%. I go to my airplane right now, and even though I have a sealed Concorde battery, and I pop open the battery box and look at it, I guarantee you there's going to be some corrosion on the leads. It is every single time. Even on NICAD batteries. I told y'all my story during basic electricity during aircraft batteries about blowing up my knife trying to clean off the corrosion whenever I was like 19. It was a NICAD battery, a sealed, high state-of-the-art battery, and it still is susceptible to corrosion. So you're going to 100% see corrosion in battery compartments and around batteries. Okay, so bilge areas. These are natural collection points for hydraulic fluids, water, dirt, odd ends of debris. Now, I always tell these stories about taking a South China Air 737. When I worked at an MRO, we would strip them down, then we'd sell them to aircraft or Part 121 carriers in the U.S. Whenever we pulled the blankets out in the bottom, there was always a bunch of junk inside, like just that somebody had dropped or whatever, and eventually all things lead to the bottom of the airplane. Those bilge areas like that will 100% lead to a lot of corrosion. Anywhere that there's like a place where fluid and stuff can get caught, there's your electrolyte to cause corrosion to begin. And so like look for those bilge areas. Lavatories, buffets, and galleys. Why? Because there's water going through them, all of them, and they will absolutely corrode, and that's something that you need to keep in mind as you start doing inspections. A lot of times, like you get to like a lot of your heavier checks, they'll call for them to be removed, inspected, and serviced, and put back in. And so removing them is not really that big of a deal. They actually come apart pretty easily. But like that, it is a place where you'll end up finding a lot of corrosion, blue water, regular potable water, all kinds of stuff. Okay, wheel well and landing gear. So especially like on a 3.7, the landing, the wheel well is exceptionally dirty. It is on just about all aircraft. Why? Because, well, that's where all the dirt's getting flung up into. Imagine like you look at the wheel well of your truck and there's like mud and stuff on the inside. It's no different than an airplane. The only difference is the airplane generally works in a cleaner environment because it's on an airport for the most part, unless you're doing like a bunch of bush flying stuff, and that's its own beast unto itself. And so like your wheel wells are always going to have a lot of corrosion, or at least a lot of potential for corrosion. You might clean it out and might not be anything in there, but given enough time, eventually it will have a lot of corrosion. Water entrapment areas, design specifications require that aircraft have drains installed in all areas where water may collect. So like an example of that would be the bottom of a engine cowling will always have a drain, so that way anything that gets caught in there can escape. But either way, those areas where it's always kind of at the bottom of whatever will almost always have at least a corrosion tendency, if not outright like this is corrosion going on. Okay, engine frontal areas and air cooling vents. You'll see this too, especially on recip engines that fly around salt water. The cooling fins on the very front seem to corrode before the rest of the engine does. Reason being, my guess is that it catches a lot of the salt water first, and or the salty air first, and that's where it starts. But yeah, look around those areas and think about a cooling vent. It's not too different than a tailpipe. It's going to expand and contract. It's going to expose itself to surface or to atmosphere, and that's going to lead to corrosion. Okay, wing flap and spoiler recesses, it's no different than the water entrapments. The spoilers and the wing flaps are going to go up in their own little areas, or the spoilers are going to sit down in their own little kind of cutout. Those areas are often, for one, they capture things and they hold things. They're like a little container. But number two is that they're also often overlooked because you have to have the flaps or the spoilers deployed to be able to look inside there and actually clean it out. And a lot of times there's just not time for that. They turn it at the gate and off they go, and they're waiting for their annual checks to get those things cleaned out. External skin areas, external aircraft surfaces that are readily visible and accessible for inspection and maintenance. Even here, certain types of configurations and combinations of materials become troublesome under certain operating conditions that require special attention. So anything that is exposed, so even like a painted aircraft surface can have corrosion. And so whenever you're doing your general visual inspections, your GVIs, you're looking at like rivet lines, and like so it's always good to like look and then clean with your hand, like take a rag and run over the top of it. If there's any sort of corrosion and stuff, you will generally either see it or you will feel it, and it'll look different than everything else, and you'll know that it's there. But those are all areas that you could end up having corrosion areas. There's a couple more that they really flesh this out pretty well. Relatively little corrosion trouble is experienced with magnesium skins with original surface finish and insulation are adequately maintained. But the moment that you start to tamper at the surface, such as any sort of work on it, you'll end up having corrosion potential there. Piano type hinges are prime spots for corrosion due to the dissimilar metal contact between the steel pin aluminum hinge. Also, it will trap dirt and things like that. So like on the Aztec, the engine cowlings have a piano hinge joint that comes down. I'll tell you that like it seems that as time goes on, people get farther and further away from the piano hinge, both because it's just a hassle. It's like they're not fun to really mess with, but they're also a corrosion powerhouse. Corrosion of metal skin joint by spot welding is the result of the entrance and entrapment of corrosive agents between the layers of metal. So yeah, like anywhere that there's two metals coming together, you can bet your bottom dollar that there's going to be definitely a chance for corrosion in there. Okay, so electronic and electrical compartments. So electricity really speeds corrosion along. Like you really need an electrical charge to make it happen. And so in a lot of times that's static electricity in the air, but like if you have a lot of electricity going through an area, you're gonna end up having a lot of corrosion. There's a reason why your battery leads corrode so easily, so readily. It's because you have dissimilar metals right there. You often have some sort of electrolyte, and then you have a ton of power going through there. So that power feeds the corrosion. Electricity just basically puts everything in fast forward mode, and you'll see what happens. Okay, miscellaneous trouble areas. So helicopter rotor heads, gearboxes, in addition to being constantly exposed to elements, contain bare steel surfaces. All control cables. So like you always want to like run your hands down control cables and see like if you can find any loose wires, any sort of corrosion or anything else like that. One of the best ways to inspect those is take a shop towel, bend it over the top of it, and run them down it. If there's anything that's going crazy, the shop towel will 100% let you know. All right. And so, so that is your, water entrapment areas. Okay. Yeah, so those are your air or corrosion areas that are very prone to, or areas on aircraft that are very prone to corrosion, very susceptible to corrosion. A lot of this is that you just need to start inspecting and finding things. The more you do that, you'll start to kind of get like a sixth sense of what looks good, what looks bad, and what could potentially be really, really corrosive, and what's probably okay. Okay, so before we really kind of dive into working on treating corrosion, let's talk about dissimilar metals right quick. Now, there's multiple scenarios in an aircraft where you have two different types of metals that come together. I mean, even you might have different electrical contacts that are butted up against like aluminum, pins and different things like that. Probably not the best example, but the point being is that there's tons and tons and tons of different scenarios where you could have one type of metal touching another type of metal. So how do we keep dissimilar corrosion from happening? Well, there's two kind of camps. There's dissimilar metals that involve magnesium and dissimilar metals that don't involve magnesium. The ones that don't involve magnesium are pretty simple. Everything will be basically sprayed down with a substance called zinc chromate, and you'll get to know what zinc chromate is pretty easily in here because everything inside of an airplane is basically yellow, and that yellow is zinc chromate, and the reason it's there is corrosion. It's a corrosion inhibitor. So you spray it down once, you spray it down twice. If it's on the outside of the aircraft or something that you want to look pretty, you'll put primer on it, then you'll put paint up till however many coats that you need to get it to look pretty. So that's non-magnesium dissimilar metal protection. The next one is zinc chromate or magnesium. Magnesium basically gets the two layers of zinc chromate plus a little bit extra. So you'll have a layer of pressure sensitive vinyl tape that's 0.03 of an inch thick. Is applied smoothly and firmly to prevent air bubbles and wrinkles. To avoid a creep back, the tape is not stretched during the application, so it's just easily put on, super duper slow. When the thickness of tape interferes with the assembly of the parts, and when relative motion exists between parts, when service temperatures above 250 degrees are anticipated, the use of the tape is eliminated and extra coats, usually 3 of primer, are applied. So essentially, If it is magnesium, you get 2 layers of zinc chromate plus a vinyl tape that goes on top of that. If you can't put the vinyl tape on top of that, then you just prime it to no end with primer before you paint it. And that's what you do for magnesium. Now, almost all of these dissimilar metals have some sort of barrier in addition to the zinc chromate that will keep the metals apart. So the separating materials may be metal primer, so that's what the magnesium, so we're going to prime it before we paint it, and that could be it. Aluminum tape, you'll hear go fast tape, or what's the other term that people use for it? But essentially, speed tape. So like you'll see speed tape. There's like social media reels going around of these guys that there's duct taping the engine cowling. That what they're putting on is speed tape, and speed tape's actually pretty gnarly stuff. I've seen it do a lot of things that you wouldn't think that it would be able to do. So that's an option for you. Washers, we've talked about washers, especially like little plastic washers that help keep metal parts and pieces apart. Grease is one that we haven't really talked about. So greasing parts has several different functionalities that go into it. Its primary is usually to lubricate and to cool, but it also can be to simply keep things from touching one another. That both those metals don't react to the grease, and the grease can stand in the middle and kind of keep those two metal pieces apart. That's an option. Sealant, you'll use a lot of sealant. We haven't got to the sealant part of our lives yet in this course, but you'll see a lot of sealant being used of different varieties all over the place. Black RTV, B1.5, those types of things. But yeah, so like essentially, like in order to protect against dissimilar metal corrosion, which there's a lot of on aircraft, you always want to have things separated. You generally, just as a general rule, want to keep things from touching one another. That's just kind of like a rule going forward, is that like things don't really get along. And so if you don't ever want to have metal to metal contact, it's generally bad. So you're going to have some sort of separation in there, be it a grommet, be it an Adele clamp or some sort of standoff, or maybe even take like a bunch of high temp RTV and you RTV a whole thing up, and then you set the line or metal or whatever it is that you're trying to separate it in there. And that RTV, as it sets up, it starts this like kind of like a springy sort of like a flubber like mass that adheres to one side of it, and that will provide the separation that you want. That's especially used in like you'll see a lot of that in like GA, where you have like fuel lines going next to engine mounts, and they're like, well, what do we do here? Instead of they'll clamp it, they'll RTV it. Not the most professional way to get it done, but it is effective. And so like that's how you protect against dissimilar corrosion. Okay, so let's talk about some special case scenarios before we get into how do we fix corrosion once we've found it. One of them is a misapplication of cleaners. Now, we in our aircraft wash class, we talked about how there's a lot of different cleaners that are out there, a lot of different solvents and detergents and things like that. And that it's kind of a science unto itself, that like a lot of times the guys that clean airplanes, for the most part, are they're specialty people. And that's why. It's because there's so many options out there that it becomes like its own subset of aviation. Now, the consequences of not having that expertise can be pretty drastic. If you take the wrong cleaner and you apply it to an aluminum surface, you could have a situation where you take the protective coating or the annealing off of the aluminum and expose it to the atmosphere, and it causes corrosion. But even that will still take some time. Some cleaners can be so aggressive that it will corrode the metal themselves. And I've seen that where somebody went and like completely destroyed an airplane because they used the wrong type of cleaner on there. Now the cleaner worked and it was great, and it cleaned it all up, made it look a little pretty. But like, man, within a couple of days, all of a sudden you start to realize there was a mistake that was made. The same thing can happen with composites. If you think this is becoming a bigger and bigger thing because more and more aircraft are starting to go more and more composite, If you take the wrong solvent and you apply it to a composite aircraft, it could cause it to delaminate and just effectively break apart. And as we saw with Hawaiian Air, is that like corrosion happens with a extremely vertical inflection point. That like all of a sudden like it's not really that bad, it's not really that bad, that all of a sudden it's way bad, like just like over no time at all. So you have that's really, really dangerous, especially with composites, because you have such a narrow window to find something so small that could be something that would be really, really drastic. So you think about if you use the wrong cleaner on a 777X wing, what would end up happening? At what point would we start to pick up on there was something wrong with the wing before the wing just flew off in midair? So it's extremely important, especially with composite aircraft, to be very, very selective with anything that you put on that aircraft. And then even more so with aluminum, because you'll cause corrosion, and the corrosion will cause failures. So you must use the right tool for the right job, and in this case, the tool is a cleaner. All right, so how do we inspect for corrosion? We know what corrosion is now, and we know what causes it and what it looks like. What's the inspection process look like? Well, generally speaking, is with these two eyes and these two hands. So you're going to look at things and see if you can spot corrosion, and that's why it's really important for you to understand the different types, to understand how it manifests, what it looks like, and what the different metals are. And we'll put a chart up to let you kind of review the different types of manifestations of corrosion on the different types of metals. So you have like copper that will always turn out to be green, and iron will always be this orange-brown, rusty color. Aluminum is white chalky substance, that sort of thing. And then you have all your different types of like filiform, fretting, intergranular, so on and so forth. Like that's why it's important to know those types of things. So that way you can spot it, and you can also touch it with your hands and know that, hey, like this isn't right. And then there's a certain element of that just goes beyond academics. It comes with experience of finding it on a regular basis. To knowing like, that's pitting. I can see it pitting from a mile off because it's so obvious. But once you got to the point where you can't see it or touch it or feel it anymore, how else do you get to it? Well, your mirror and a flashlight will get you into like crooks and crannies, but that'll only get you so far. And a lot of times corrosion will often be found via NDI. So that's either ultrasonic, dye pin, mag particle, what have you. Whatever your flavor of non-destructive inspection, non-destructive testing is, or whatever the book calls for in that moment, or whatever your company has available to you, that's how you would want to employ it. But either way, it all starts with a trained technician that knows what to look for and knows what to feel for, and then once you go beyond that, that's when we get to the technical stuff. But most of that stuff is baked into the maintenance process, so you won't necessarily have to call out for NDI or have to go like do it yourself. Most of the time, like you're just going to be doing a general visual inspection, a GVI, and I'm going to start saying GVI more often, but you're going to be doing GVIs, and then only on condition do you call for NDI. But most of the time, you'll find it without, and you won't need NDI. It's only kind of in rare circumstances that you actually have to go that far. All right, let's talk about conversion coatings real quick. Conversion coatings that you'll see primarily in aircraft, or like we've already talked about, zinc chromate. It's yellow. Essentially, all a conversion coating is a part that's not going to be painted like on the outside of the airplane. They still need to be protected against corrosion, and so they take this piece of metal, this part, they acid wash it and get everything off of it, and then they prime it with whatever the conversion coating is. Like I said, in our case, it's typically zinc chromate, but there are others that are out there as well. Just zinc chromate's the most common one. The whole idea with the conversion coating is that like you have the metal. So like you go back to our corrosion triangle, you'll have metal, and then you have water and oxygen that it could potentially be exposed to. So if we can cover that metal up, we effectively just remove that from the triangle, and then you can expose it to as much oxygen and water as you want. As long as there's no metal coming into contact with it, it doesn't really matter. It won't corrode, and it is by far probably the most effective way to control corrosion on an aircraft. Most of the time that you see corrosion on aircraft, especially like GA aircraft, is because they skimped on the corrosion coating part of it, and you don't see any zinc chromate. If you open up a military aircraft or commercial aircraft, something that's there to make money or do a job, and not just like a hobby type thing that they want to keep the cost low, you'll almost always see zinc chromate parts. Okay, so let's talk about some steps for just preventative maintenance. How do we prevent corrosion from manifesting inside the aircraft? First off is adequate cleaning. Adequately cleaning the aircraft. That means taking some ownership in the aircraft. That's the number one thing that will prevent corrosion, is that you actually care about it. So if you go and you see a bunch of trash on the side of the plane and you wash it off, you're going to help prevent corrosion. If you go through whenever you're working and you see a bunch of trash in the plane, and maybe there's left for some other job or something's deteriorating or whatever, and you clean it up, that will help prevent corrosion. If you spill something and you clean it up correctly, that will prevent corrosion. If you do your job right and you torque everything down and everything is in order and everything is taken care of per the standard, you'll prevent corrosion, because guess what? The whole system is designed to help prevent corrosion. It just matters whether or not somebody cares to actually do it the right way. Number 2, thorough periodic lubrication. Staying on top of the preventative maintenance of the aircraft will help prevent corrosion. A lot of times corrosion is set up because things aren't greased, things aren't lubed, things aren't cleaned. So if you simply just do what the maintenance manual tells you and you stay on top of it, you will prevent corrosion. Detailed inspection for corrosion and failure of protective systems. So basically, like if you are following the maintenance manual and you're doing your job correctly and you're inspecting to standard, you will find corrosion as it starts to manifest and remove it, and it'll never really become a thing. There are plenty of aircraft that have been flying since before World War II that are out there right now, and they're only flying because one guy decided to take care of it. That's all it really boils down to. So make sure that whenever you're doing your inspections, take them seriously and know that there's consequences to your actions, both whether or not you do it correctly or you don't. Number 4, prompt treatment of corrosion and touch-up of damaged paint areas. Don't let the paint get chipped, because if the paint gets chipped, then it's going to corrode because you're exposing that metal to the atmosphere. Accurate record keeping and reporting material or design deficiencies to the manufacturer and the FAA. So accurate record keeping basically boils down to making sure that you stay on top of the maintenance schedule. If you don't know like how many hours the aircraft has on it, or you don't know when the next inspection's due, how can you stay true to the maintenance manual if you don't know what the current state of the aircraft is? Okay, use of appropriate materials, equipment, technical publications, adequately training personnel. Right tool, right job. Going back to what we were talking about with the using improper cleaners, this is the same thing. If you use if you don't know like what the right thing to do is, and you just use any old thing off the shelf, you could cause a reaction that doesn't take the corrosion off, but it just makes it way worse. So make sure you're using the right thing. The way that we know the right things, we have the right manual and we have the right people that are doing it. It's not just somebody off the street, it's somebody who actually knows and cares about what they're doing. Okay, maintenance of basic finish systems. This kind of goes back to the whole chip paint thing. If you see some damage on the aircraft, fix it. It's really that simple. Keeping drain holes free of obstructions. So if the drains are there for a reason. If the drain is clogged up and it backs everything up, everywhere that liquid, whatever type of liquid it is, it's touching is a corrosion hazard. So make sure that the drains work. There's drains on everything, like everything on the aircraft. It doesn't matter what aircraft it is. If you just go look at it, you'll see drains. So that way, like little bits of fluid and all this other kind of stuff can escape and be gone. The reason why they're there is so that way that fluid doesn't just coagulate and just sit in some area causing corrosion and other problems. So make sure that the drains work. Number 9, daily draining of fuel cell sumps. So you'll be required to sump aircraft fuel cells. We have a flight going and we have a bunch of Cessna 172s or Piper Cherokees or Archers or whatever the scenario is. Go underneath them and you'll sump the fuel tanks. When you sump those fuel tanks, all the water and trash will come out. By getting that water and trash out, you're preventing corrosion and a list of other issues as well. Daily wipe down of exposed critical areas. So like an exposed critical area would be like the struts. Having the internal strut that goes up into the strut that's nice and shiny, isopropyl alcohol and a rag every day, making sure it's clean where you should be able to shave off of looking at that strut. Sealing of aircraft against water, against foul weather, and proper ventilation on warm, sunny days. So that means that you don't leave the door open, you don't leave the windows open. Nothing that is open and exposed should be cracked, and it should be hangared. It shouldn't even be in the rain. But in case that it finds itself in a situation where it's exposed to rain, it shouldn't have like the door open so that way just water can come in. Because once water comes in, water gets where it's not supposed to be, and it'll cause corrosion. Replacing deteriorated or damaged gaskets and sealants to avoid water intrusion and entrapment. On the 58, this was a big one. We used to go through yards of weather stripping because it didn't seem to matter what happened, the weather stripping always got ripped off. But the weather stripping is important because that door would seal if it was the crew doors or on the avionics bay door. That would help prevent getting dust and water and junk inside of the helicopter. And the more you kept that stuff out, the better the helicopter operated. You were doing yourself a favor by simply just maintaining it. Okay. And then finally, maximum use of protective covers on parked aircraft. So put the flyaway gear on. If the aircraft is parked, pitot covers come on, engine inlet covers go on, drape over the windshield windscreen cover. If any of that stuff, if you have it, use it. If you don't have it, buy it. So that way it's a little bit of cost and expense and hassle up front that could save a big cost and a big expense and a completely derailing hassle on the back end. But that's preventive measures for corrosion. Okay, so what do we do if we find corrosion somewhere? So the corrosion itself has to be removed, first off. Now this can happen in a variety of ways depending on the situation, depending on your accessibility, the time that you have, what resources you have available, what it's on, what type of metal it's on. All of this is going to vary, and it'll probably be dictated somewhere in the maintenance manual that if any corrosion is found, remove it and then give you a document. But generally speaking, this is what will happen. If you find corrosion somewhere and it's slight, you'll want to just to remove it via like an SOS pad, a crocus cloth, sandpaper, that kind of thing. You just blend it out, and so that way, like you restore you remove the corrosion, you blend out the pitting, so that way it is close to its original state as possible. Remember our discussion with the TCDS and this is the state of the aircraft that we've certified. Your entire job as a maintainer is to try to maintain that TCDS. So you're always going to be going back to that scenario. This is no different. If you find corrosion on a piece of metal somewhere on the aircraft that's outside of the TCDS standard, and you're trying to return it back to its original state. So you're going to turn around and take your sandpaper and sand it off. Maybe you use an air ratchet with a disc on there if it's super duper serious. Now keep in mind you don't want to go too crazy because then you don't want to damage the aircraft further. You just want to try to get it back to its original state as possible. There are some opportunities where you can turn around and use chemical cures for that, where you'll chemically remove and etch the surface, so that way you remove all of that corrosion and get it all out, and then you can come back and like prime and paint and restore the state of the aircraft. You'll come in with like zinc chromate, hit that as a primer, and then paint over the top of it if that's the case. Now, if there is, more damage than can be repaired, it'll be time to remove and replace. You might be removing entire panels, and that's where things start getting expensive and things start getting very, very involved very quickly. Is when you start taking out structural panels due to corrosion. But that may be what has to happen in order to restore the aircraft. Generally speaking, anything that's rusted just needs to be replaced. Most of the time it's hardware, so it's not really that big of a deal to replace it. You're just gonna simply say, hey, look, this screw is corroded. You're gonna take them out, clean up the area as best you can, put it back in. It can also happen with aluminum. Generally speaking, replace anything that's corroded if you can. I only really delve into the let's try to correct the metal and try to restore the metal kind of modality if it becomes cost prohibitive for you to do it. So for instance, on my airplane on the left hand side, inside the inspection panel, there's some corrosion on the spar. Well, it's not really that big of a deal, and so we just took it off with some sandpaper and then shot it with some CPC and then and called it a day. That's about the best that you can do. And then we'll monitor it as the annuals progress. And if it gets worse and worse and worse, then it may be time to do something drastic, like replace the wing. But generally speaking, you'll want to try to avoid replacing, very expensive parts that's going to require a lot of work to do, and it's going to be very expensive to just simply buy the part and mount it. But as a rule of thumb, always replace corroded parts if you can. It should be fairly easy to do most of the time. If you end up having to blend some stuff, then okay, but don't get too crazy with it. There's a kind of a mechanics value discretion that has to happen, some sort of decision that has to happen whenever you go too far, where it's like, hey, look, this whole wing is just ate up, and maybe it's time for a new wing. Okay, CPCs are a wide range of things that are out there. So I'm just going to start just kind of going through several different ones, but know that there's more out there, and they can be used in different applications depending on the situation. So first off, from a general aviation standpoint, one of the ones that you'll use is an aerosol spray called LPS3. There's a mil spec that corresponds with what LPS3 is, but essentially it's a waxy sealant, and you'll see LPS3 used on any number of places where there is stress, movement. It's also a lubricant that can go on to I don't know, where the bolt that connects the flap to the control arm. That's an example of one place that you shoot with the LPS3, at least on the Piper Cherokee. Those effectively, those have to get applied pretty frequently because they get worn off. So anytime that you're doing 100-hour on the aircraft, you'll end up inside the aircraft. It'll have or inside the maintenance manual, it'll have a certain lubrication points, and it'll tell you lube this with something that complies with this mil spec or whatever the standard is. And so in the case of LPS3, you'll use that and you'll hit those lube points as you go. So that is an example of one. The bigger, more complicated airplanes, the more type of solvents and lubes and different things that you're going to have to use to service them. So just bear that in mind. Smaller airplanes, there's just less of them, so you end up being able to consolidate down to just a couple. So that's LPS3. There are called thin film dielectrics. A lot of times those are they are dielectrics that are put on parts that eventually go on aircraft. Not something that you have to service on a regular basis. You just know that you need to preserve that film that's on there. But that is a type of CPC that's a corrosion preventative compound, an inhibitor that takes the metal out of the equation, just like our zinc chromate does. Very, very simple application to that, and not something you have to service. So you'll take note of it if there's a scratch or it's been removed or whatever, because that opens up that part to corrosion. But if it's all encompassed in that film, then you generally don't have to worry about it. You just kind of GVI it and move on. Other types of CPCs that are out there and available on the market. One that's very, very popular is Corrosion X. So whenever we were building seaplanes, we would get the plane from the factory, we'd open up all the panels, and then we would Corrosion X the side of those panels because they're going to be operating over water in salt and stuff like that. And we would do it in the floats too. We'd open up the floats and Corrosion X them. What Corrosion X effectively does is it's kind of like your LPS3 or even really kind of a thin film sealant like that. It is an aerosol that goes in there a lot. You can get them in big jugs that you hook up to shop air and you spray it in with a nozzle. Not good for you to inhale, so don't do that. But it goes into the part, and then it settles on the metal, and you'll even see like this kind of green film where Corrosion X is sitting, and that effectively creates a hydrophobic barrier. Hydrophobic barrier that keeps the water away from the part and seals it so that way corrosion can't get in there and get started. So that's one of them. My favorite CPC that I've ever found is, and I'm going to mess this word up because I've never been able to say it right, but it's called Berry-Coat. It looks like Castro or K-Row, like, you know, the super thick syrup that you buy in the grocery store for pecan pies and things like that. And what we would do is we would take a little cap, we'd fill this stuff up, and then on floats, whenever we go to seal them, we would put our hardware on, and then we would come back with that stuff and we would dip it on top, and then we would take it off. And it was so thick that sometimes we'd have to put it in the microwave to kind of get it loosened up a little bit, so that way we could actually apply it. Because the idea being is that it was like this goopy, super thick stuff that you would put over the heads of bolts, so that way whenever the water splashed it literally physically was never going to get in there, because that stuff was so hydrophobic and so thick that it would be there forever. If you do all this stuff right on the front end, then you don't really have to worry about corrosion pretty much ever. The thing that really kind of set this up for me is working on seaplanes was that we would get these planes that customers would bring in, and they'd want us to do an annual on it, and we would have to beat off like bolts and chisel them off and use impacts to try to get into just access things, replacing screws all the time. There's corrosion everywhere. They're just ate up, and the customer's just like, yeah, well, that's just how it is. But then we would get planes back for annual that we had installed the floats on and done all this corrosion work or anti-corrosion work to, and it would go by so quick because there was just no corrosion. Like we would have to contend with getting all that Pericoat off, and then we'd have to re-corrosion next. And there's little things that would just kind of eat up your time, but it was nowhere near the amount of hassle of the corrosion in the floats from these randos that would just show up at the shop. And so you start to kind of to understand those, that if you just take a little bit of time up front to do it correctly, that airplane is going to be in much better shape for much longer, and it's going to save you a ton of time, and if you're the owner, a ton of money, by just simply doing it right on the front end and taking the extra little bit of time to add the extra little bit of preventative measures, so that way you don't have to pay the piper whenever the annual rolls around again. Okay, so what is the right CPC, and how often do we put it on there? So the right CPC is pretty simple. The 100-hour inspection list in your aircraft's maintenance manual will tell you. It will say hey, look, every 100 hours do this, apply this lubricant, apply this CPC, whatever, and it'll give you if they don't give you an exact product, it'll give you at least a standard that to shop products on. So that's how you know. LPS3 goes to mill standard, whatever it is, and so whenever you see that mill standard, whatever it is, you just no, that's LPS3. And I actually printed all that stuff out and then translated it into product names, so that way I don't have to do that thinking anymore whenever my 100-hour rolls around. And so you'll learn to do that. A lot of times, if you're working in a big company, you'll have a task card, and the task card will already have done all that for you. And what's happened is that somebody in production control or some sort of engineering body has gone through the maintenance manual and said, okay, this is what we need to do at this time, and that's how they build the task card, and they do what they call job planning, and that's what they do for you, so you don't have to really mess with it. So a lot of times, it's just simply written down. You do what you have to do. If you're in weird situations like with seaplanes, then you kind of like learn through the school of hard knocks. Like first off, you go with whatever the float's TCDS, actually like will say, like whatever's in the float manual, you'll put that on. The aircraft manual, you'll put that on, and then just through experience, you'll learn, we need to also corrosion X the inside of the float, or we need to put the paracoat on so that way we can seal the bolt heads, because this is a common corrosion point. And so you kind of like start to experiment with that. Now AC 43-4 will actually tell us how often an aircraft is supposed to be inspected for corrosion. And in theory, if you're inspecting for corrosion on a regular interval, then you should also be inspecting the corrosion, the anti-corrosion coatings that are on these parts. And also, if there's corrosion there, removing it. So that kind of gives you an idea of where you're be at. But ultimately, your aircraft maintenance manual should have all this incorporated into it. But if not, we're going to read through them. Okay, so frequency of inspections is Chapter 5 of 43-4 of the AC 43-4. It'll say aircraft operating in a severe environment should be inspected every 15 calendar days. So the way we got around that with the Army, instead of every 15 calendar days, we did it every 10 hours, and we were flying at least an hour a day. So we were actually exceeding the standard on that. And a severe environment, it was basically a corrosion severe environment. So like whenever we were at a Hunter Army Airfield in Savannah, Georgia, we were always flying within 10 nautical miles of salt water. It was considered a severe environment. And so we were doing engine washes, we were doing preventative maintenance services every 10 days, and so or every 10 hours, and so we were getting through these inspections a lot more frequently. But if you're the maintenance guy for, say, a private jet, maybe every 10 days you're having to figure out, like, okay, or every 15 days, every 2 weeks, you're open up the cowlings and looking in there and make sure, like, no corrosion, we're good, and off you go. Okay, aircraft operating in a moderate environment, 45 calendar days. So a moderate environment would be Texarkana. It's like there's water here, it's not really that bad. It's like the temperature swings aren't generally that crazy, and it should be an okay environment to operate an aircraft in. So every 45 days you're doing that. Okay, aircraft operating in a mild environment every 90 days. So think like Victorville, like California, or some desert town somewhere, Las Vegas. That's a pretty mild environment. It does get hot, so that's something that you have to kind of think through, but there's not a lot of moisture in the air, probably not it's definitely not a place that you really worry about corrosion that much, but it can still happen. So also some kind of best practices that they put in here, that aircraft should be washed prior to every inspection. So you should be washing the aircraft pretty regularly. Now that kind of comes with a trade-off, because you don't want to introduce water into an airframe that would otherwise be waterless, but also you can't really inspect things that you can't see, and so you have to clean. So you have to use your judgment on that. So crews familiar with corrosion problems and treatment should perform corrosion checks. So we're making you familiar with corrosion problems and treatment. We're going to do so more in class. And then operators of infrequently flying aircraft should develop a calendar-based corrosion inspection and repair program rather than basing on flight hours. Because of uncertain operating environments, make adjustments to the calendar time inspection interval after analysis of corrosion inspection findings, which is the majority of your GA aircraft, that they should be done on a regular calendar basis rather than on a flight hour basis. So really every 90 days, or once a quarter, you should be opening up the panels on your airplane, looking for corrosion, and putting it back together per AC 43-4. But anyways, that's corrosion. It is a fantastic natural phenomenon that we have to contend with. And you'll actually learn more just simply by looking at corrosion and getting your reps in than you will from any sort of like academic, like me telling you about corrosion is one thing. You finding corrosion and fixing corrosion, you'll start to get it like really fast. Don't let any of this intimidate you. It's actually pretty simple. And look forward to seeing you in the hangar. We'll fix some of it.